Good afternoon, everyone. I'm Christopher Pasqua, and we're the MPS Storage and Retrieval System Group. And today, we would like to show you what we as a group have accomplished in the past 14 weeks. Presenting with me today is Rommel de Valmoite, Christopher Alvaro, and Corin Baliwan. Please hold any questions you may have at the end of the presentation, as there will be a designated slide for that. We will be discussing our overall progression as a group, the problems we have encountered, and how we ended up finding a solution for the adversity we faced. Now to start off with the presentation. An ASRS or automated storage and retrieval system, unlike the conventional means of using a manual labor to store and retrieve items, which can expend quite a bit of energy, but it can also increase the price of a product, which is not very suitable when there are competitors involved. Owning an automated storage and retrieval system also conserves a large shelving space, as constant flow of inventory exists as we live in the age of having anything we desire is easy to obtain using the internet. Another advantage of utilizing an automated system with constant flow is having all inventory that passes through the system saves a large portion of time as it is cataloged. As you can see to the right of the slide is the final layout of our system is going to be looking like. Starting from the front of the station is our storage device that we've designed and 3D printed. And at the back of the station is the 5-axis Mitsubishi robot arm that we've been provided to be integrated in the system. We'll be discussing a more in-depth detail in the later slides. For today's presentation, we will be discussing the design concepts, final design, the difficulties we encountered, the case study, the GD&T, the functional diagram, the mechanical diagram, and finally the pneumatic diagram. I will now discuss an overview of the problem statement discussed by us and our client. The points discussed are what we and our client agreed upon for the project specifications. This includes making a fast and efficient system as agreed by the client. We would like the system to store around 20 to 30 pucks of each color, and it was settled that the robot is to retrieve 10 to 12 pucks in a single cycle. Another point discussed was to have 3 different colored pucks to be separated to their respective storage device. By doing so, the use of various proximity sensors are used. The next point was to develop and create a suitable end-of-arm tooling for the robotic arm. If you look closely to the image to your right, we were able to create a picker-style tool that conforms to the shape of the puck. Another point discussed was to create a storage system that works in line with the robotic arm. Because of its limited mobility and the possibility of a collision is possible, so having a top load was kept in mind. With the limited space provided and the limited movement made by the robotic arm, planning to use the majority of the space front space is used to prevent large movement from occurring, saving time and preventing any possible collisions. And the final point is to make the system user-friendly to operate, as having easy access does not require any special training in order to operate the system. While designing our storage device, we had to keep in mind to store as much inventory as possible with the space provided. We also wanted to store the pucks by color. Since it's part of the MPS workstation, we planned on using capacitive, inductive, and optical sensors to identify each of the 3 colored pucks, being red, silver, and black, to be brought to their designated storage. On this slide, these were some of the concepts we thought of using for the workstation. We've come up with a stair-based storage, a festo-based storage, 2 types of angled slide storages, a stacking magazine-style storage, which we found best, and the majority of these would be great options, but due to the limited space and the limited movement from the robotic arm, ideas such as the staircase, slider, and festo stack storage did not make the cut.
Our first concept utilized a magazine-fed style storage system. The drop-off point for the puck to be stored is at the top of the magazine. When a puck is to be retrieved, a pneumatic piston will push the puck to the designated pickup point. Though it can store a lot of pucks, vertical space is limited for 3 devices to be parallel with one another. So collision between the robotic arm and the storage systems can occur, as well as horizontal space taken up by the incline and the piston was another issue when designing the overall layout of the system, as you can see by the drawing in the bottom right of the slide. As you can see by the prototype of the top at the top, the incline was removed from the concept to save vertical space.
Our second concept only involved a magazine storage system. Like the first concept, the drop-off point for the puck will be at the top of the clip. However, we added a secondary slot for storage. When a puck is needed to be retrieved, a pneumatic piston pushes a puck directly to the pickup point. At this point, we decided to remove the use of a slider with the magazine as a vertical space was being an issue. So to counter that problem, we incorporated the slider within the magazine. So having to use a buffer to separate each puck to the pickup point was unnecessary.
For the final design for the storage system, We decided to keep the piston case as is, and decided to add an additional slot to maximize the agreed upon storage size per each color of 30 per storage device. A decision was made to have an incline to at the top of the magazine. Each of the three slots gets filled, the first being the closest to the drop-off point, all the way to the end of of the main slot, where the pneumatic cylinder will push the puck when the system requires it to do so, letting gravity do all the work when letting each puck drop.
While in the designing phase of our device, we encountered quite a bit of problems. This includes 3D printing errors, as you can see from the images on the slide, from the piece being shifted while being created, as well as geometric issues. For instance, while creating the internal slope design for the magazine for Design Concept 2 and Final Design, we encountered problems with geometry and jamming within the cylinder, as well as the puck not being in the correct orientation when traveling down to the pickup point. As you can see by the simulation done on SolidWorks, a jam occurs in the third slot. By using the motion analysis function on SolidWorks, we can demonstrate what the final assembly will function like. The study was conducted when the puck slides in the receiving area and when the puck slides in the storage system, which is what you're seeing right now. To be more efficient, we use gravity to make the puck slide in its destination. In the study, it showed us what is happening frame by frame. With this, we can identify what is happening in the assembly. With trial and error, we found the best angle at which the puck slides smoothly and made certain adjustments within the part. This is to make sure that the puck will not change its orientation when dropping, which happened in our prototypes. Motion analysis is very important because it helps us reduce cost and waste. In our case, one stacking magazine takes about 2 days and 11 hours to 3D print. It uses about 110 meters or 321 grams of spool. So that is 1/3 of the spool already. So we made sure that our finalized part works the way we want it before 3D printing it.
For our final design of the stacking magazine, we carefully applied the geometric dimensioning and tolerancing on detailing and dimensioning to make our final design meet all the requirements for a fully functional storage system. As you have noticed on our drawing, there are some datum points for us to be able to use as a reference plane for GD&T. For datum B and D, the flatness tolerance should be kept. This is particularly important so that our orientation of the stacking magazine will be maintained as per our design requirements. The perpendicularity with respect to datum D should be followed. This will ensure that our stacking magazine will fit exactly and inserted vertically on the piston case. The parallelism of datum C should be followed to keep the pack orientation always maintained throughout the sliding sequence. The circularity tolerance which controls the out of roundness of the stacking magazine should be kept to make the entry of the pack extremely smooth and accurate. The most important tolerance is the angularity with respect to a specific datum should be maintained. This will control the sliding motion of the pack while on the stacking magazine. So for this functional diagram, the functional diagram is the final walkthrough of our project should be able to do, which is to store and deliver products. As you can see on the diagram, the operation is split into two systems, the storage portion and the retrieval of the products. The product will enter the system, then the robot arm will pick it up and undergo a quality check to determine if the product is good or bad. The bad product will be removed and the good will be counted and stored in the storage area sorted out by colors. For the delivery, an order identification by color through an input signal. Then it's released from the storage area, which then picked up by the robot arm and delivered to the releasing area. Now for the mechanical diagram for our MPS station. Starting on the top, the number 1 is the robotic arm, which will transport all incoming and outgoing packs from the system. Number 2 and 3 and 4 are the storage devices that will store the 3 packs color packs. The number 5 is the magazine base where product is picked up. The number 6 is the incoming slider from the neighboring station. The number 7 is the outgoing slider to the next station where request with packs once. As you can see on this slide, this is the real world counterpart of what our robotic system looks like. You can see the needed sensors, which are the capacitive sensors, inductive sensor, and the photoelectric sensor. This will identify the fact per color. You can also see the input and output blocks, the pneumatic valve, and the cable tree that the wires will be sorted and organized.
This diagram is about the pneumatic system of the robotic storage system. There are three pneumatic cylinders to control the retrieval system of the storage system. Each puck collar will have one cylinder to be fully extended when that collar of the puck being ordered to retrieve. The sequence of activating the cylinders will depend on the PLC signal as per the collar being chosen to be delivered. On the diagram, you can see some components like air regulator, pressure gauge, air filter, valve bank, flow restrictors, and pneumatic cylinders.
So, in conclusion, we wanted to provide you all with an overview of our problem statement, our design concepts, and final design, as well as the difficulties we were able to overcome in these past few weeks, and finally, all the pneumatics and wiring that make the whole system functional. We're now open to the Q&A, but before we do that, we would like to demonstrate how the actual prototype works and see how the puck goes through the system. Now, are there any questions?
Yes, I do have one question. There's the value of simulation. Okay. What do you think that was worth to your project to be able to actually simulate and spend a lot of time doing simulation before actually even using 3D printing?
Oh, it can save so much time and resources, as you could see what you could fix in errors. And yeah.
I'm really impressed with what you did there with the simulation. I do plan on sharing it with your instructor. I think it was Lyndall. What you've done here is absolutely fantastic from both his courses. Really impressed with this. I'm even going to leave it on Greg James a little bit. I love this idea to use in future Festo projects.
No.
Yeah, you read my mind, Chris. I just wanted to weigh in. It's Greg from Festo, and really impressed with the design team. I think it's a fantastic approach that solves a lot of problems. So I guess my question is I really liked how you use the simulation software to kind of overcome and determine what the angle was. Were you able to get it functioning properly once you printed it? That you didn't get any jamming or the part being inserted upside down? Did it work?
Oh, yes, everything worked flawlessly, as you can see from the video.
Okay.
Yeah.
Very good. Awesome concept, guys.
I'll just add one more thing to that, it took for us a while to fix it in 3D printing, because in 3D printing, the supports for it was a bit of a trouble for us, learning how to minimize the supports in 3D printing help us save time as well, because if we use the support in 3D printing by the Cura software, it will take more time, more than 2 days. So that's a lot of time.
Right. Yeah, great use of technology versus, like you said, printing multiple models and determining what the angle is. It's I thought that was very creative of you. So congratulations.
Thank you. Any other questions?
No, thank you very much, group. It was a difficult challenge, and it's based on what I've seen in industry, where we don't want FIFO or LIFO, but I want to get a lot of parts in a small space. And I think your solution was quite ingenious. Thank you very much.
Thank you.